representing aqueous reactions. So there are different types of chemical equations. So a molecular equation, which is what we think of as like a regular chemical equation, is going to show the complete neutral formulas for all the compounds, just like if they were molecules. So here we have 2KOH plus MgNO3 makes 2KNO3 plus MgOH2. But what's actually going on in these solutions? This is an aqueous compound. In an aqueous ionic compound, the potassium ions and the hydroxide ions are separate from each other. They're each surrounded by water molecules and they're floating around independently. Magnesium nitrate, also soluble, also floating around, individual magnesium and nitrate ions. Potassium nitrate, soluble, also floating around. But this one is a solid. Magnesium and hydroxide ion like each other a lot, and so they're going to form a precipitate, a solid that sits on the bottom. So what we're going to do for our complete ionic equation is we're going to show all the ions, that's why it's complete ionic. We're going to show all the ions doing what they're actually doing in the solution. So these guys are separated, these guys are separated, those guys are separated, these guys are not. These are together. So that would be the complete ionic equation. We'll look at that in just a minute. And then the net ionic equation is going to show us only the things that are actually changing. So this is a little like your net paycheck, right? The gross paycheck includes all of the money, but then they take a bunch of stuff out, right? And really it's the net pay that is important. That's what you get to take home and spend. So we're going to cross out the things that don't change. So aqueous things are going to be written as ions. These are strong electrolytes. So this would be soluble salts, strong acids, and strong bases. We'll talk about that in just a minute. Anything that's insoluble, so a solid, a liquid, or a gas for the state symbol, we're going to just keep it together. And the only little tricky part here is that if we have a weak acid, that will have an AQ state symbol because it's aqueous. We're also going to write weak acids as if they were molecules because a weak acid does not ionize completely. It only ionizes a little bit. Most of it is the complete molecule, and so that's how we're going to represent it. So this is the equation that we were looking at earlier. So this would be the molecular equation, and if we want to write the complete ionic equation, this is a soluble compound, so we're going to write the lead and the nitrate separate from each other. Looking at this formula, in 1 mole of this, there's 1 mole of lead ions and 2 moles of nitrate ions. So we've got 2 nitrate ions for every 1 lead. Here we've got 2 potassium chlorides. That's aqueous, we need to split them up. We're going to get 2 potassiums and 2 chlorides. Over here, this one's a solid. Just copy it down, don't do anything. This one's also aqueous. We have 2 of these units. That'll be 2 potassium ions and 2 nitrate ions. Any questions? If you always write aqueous things as separate ions, you'll be right most of the time. The only time that doesn't work is if you have a weak acid, and that doesn't happen very often. So there's this complete ionic equation again. It's kind of on 2 separate levels because it's really long. What we want to look for is ions that don't change. These are spectators. Like you go to a boxing match, right? And there's a whole bunch of spectators. Do they end up black and blue afterwards? Not usually. I mean, hope not, unless there's a riot or something. But the guys in the ring beat each other up, right? So they don't look the same when they come out. But the spectator ions are just the same. They were watching. Or you could think of, in the analogy of going to this party, nitrate and potassium, they came to the party, as unattached people, and they're going to leave as unattached people. And you could say, well, they watched this happen. They watched lead and chloride fall in love, right? Become a couple. But nitrate and potassium did not get involved in a relationship. So the net ionic equation, we just want to show the relationships that formed. We don't want any of those spectators. Because what if lead had come with a different friend that night and had run into chloride? They still would have formed this compound. Nitrate has nothing to do with it. Potassium has nothing to do with it. If chloride had come with sodium, we'd still have the same outcome. So we take those spectator ions and we just cross them off. There's 2 nitrates over there, 2 nitrates over here, 2 potassiums, 2 potassiums. And we write down what's left. And this is called the net ionic equation. This shows the chemical reaction that actually occurred. Any questions? Consider the following reaction occurring in aqueous solution. Write the complete ionic and net ionic equations for this reaction. So, complete ionic reactions, we're going to separate aqueous things into ions. So this first one is HI. Now that's an acid, and the book hasn't told you which are strong acids or weak acids. Like I said, if you always split up the aqueous things, you're right most of the time, and we're going to be right on this one. So that's aqueous, so I'm going to split that into ions. So that's going to be hydrogen ion and iodide ion. H plus and I plus. There are 2 of those units, so I will get two hydrogen ions and 2 iodide ions. If you keep track of this as you write the net ionic equation, then there's no balancing to do at the end. Barium hydroxide. Should we split this into ions? Yes, is aqueous, right? That means the ions are separated. So there's only one of these units, so I'm going to get 1 barium ion. And I'm going to have 2 hydroxide ions. So then we go on to the product side. H2O liquid. Do I split that into ions? No. We only split aqueous things. Solid, liquid, gas, you just copy it down. This is a liquid. I'm not going to do anything to it. I'm just going to write it down as it is. And then the last one, BaI2 aqueous. Do we split this into ions? Yes, we do. So that would be barium ion and 2 iodide ions. Because that's what the formula shows me. So that's my net ionic equation. And sometimes that'll be abbreviated as NIE, net ionic equation. No, that's not the net ionic equation. I'm sorry. That's the complete ionic equation. Don't listen to me. That's the complete ionic equation. To get the net ionic, we have to identify what ions don't get involved. So what's an ion that is the same on both sides of the arrow? Iodide. I've got 2 iodides here, and we got 2 of them over there. So those were just watching. They didn't get affected. Which other one is a spectator? Barium. Those are my spectators. So I just cross those off, and the net ionic equation, which, as I mentioned earlier, is NIE, net ionic equation. I'm just going to copy down the things I didn't cross off. Is that equation balanced? Yeah. 2 hydrogens and 2 hydrogens and 4 over there, and 2 oxygens, 2 oxygens. But what's weird about it? Everything has a coefficient of 2. We could bring that down to just 1 and it would still be balanced, right? So a better way to write this one is, I guess you could say, simplifying it. All the coefficients were divisible by 2, so I'm going to factor a 2 out of it. Yes?
Are we required to do that, or is that just...
That's a good question. Are we required to do that?
The computer might be picky about it.
I would not, like on a multiple choice exam, I would not give you this as a choice and this as a choice and penalize you if you picked this one. I don't think that's fair. And, you know, if it was an open-ended question, I'd probably give you credit for either. But what you'll see, like with mastering chemistry, is they probably will want you to reduce the coefficients. Yeah. Because when we talk about a balanced chemical equation, we're talking about an equation that has the lowest whole number coefficients. So that there's really only one correct balanced chemical equation. So this is the correct one. This one, you know, we know what that means, but we could put 2,000 on each of these and it would also be balanced, right? So we could have like just a gazillion of different balanced chemical equations when essentially they're all the same thing.